All right. What we're going to do today is we're going to start out by talking about some z-score stuff, normal distribution probability, and then finish up with the confidence interval stuff. Went back and forth about like, do we need to sort of walk you through how to calculate z-scores and calculating things along those lines? And I think yes, because like this is kind of like introductory of all our statistics is sort of understanding sort of distributions and identifying points on a distribution and things along those lines. But we're going to work through it pretty quickly, okay? Because I want to have one, I want to get through all this today, and then two, I want to have enough time at the end. Interpretations and things along those lines. So I'm going to move through this first stuff pretty quickly. If there's something you don't understand, throw up a hand so I can stop to make sure that you've got it. But hopefully this is going to be recap from whatever undergrad stat class you took. Okay. So today, what we're going to be working on, looking at transforming raw values to standardized scores. This is going to be a big piece of what we're doing in terms of screening. Your computer program will do this for you pretty quickly and easily, but just want you to know where these numbers are coming from. Talking about some characteristics of standardized scores, getting into if we have a known distribution, how can we start to assign probabilities of obtaining a certain score or higher or lower, however we want to frame that. And then thinking about calculating, interpreting confidence intervals, which is really kind of the biggest, sort of most important piece of this, okay? So last week we had talked about if I have just a raw score doesn't tell me much about anything, right? But if I have a raw score plus a mean and a standard deviation, I can start to get a better sense for how representative is this score of the overall set, how far away these scores fall. But again, just that single raw score doesn't give us much information about where that score falls relative to other people in a population or distribution, okay? And this is where standardized scores start to become very, very helpful. What we can do is a standardized score gives us a single figure, get information about the mean, standard deviation of any single value. What we can start to do with these is take a look at of that score relative to others in the distribution. And then if we know what that distribution looks like, some properties of that, we can start assigning specific probabilities of the likelihood of finding that of that value or more extreme, okay? And so the kind of the classic in psychology, a really good example here is IQ, right? Achievement tests are normed so that they have a mean of 100 and a standard deviation of 15. And probably no other instrument that we use in psychological science that has the norming and the development for a lot of good reasons, because there's a really sort of complicated history with achievement testing and things along those lines. But we're much better than we are today than we were previously. But sort of the norming of these, like, it's a huge multi-million-dollar industry to go through, norm, and try and get a representative sample to say, okay, this is where people fall. We think about these scores as falling on a normal distribution, right, that we talked before, mean, median, mode all in the center, sort of nice symmetrical distribution out to the side. Okay. So when we have a unit normal distribution like this, what we're often working with is z-scores, okay? Z-scores are a standardized score. Z-score distribution, by definition, has a mean of 0, standard deviation of 1. If you have a mean of 0, standard deviation, that's how you know you're working with a standardized distribution, okay? This mean, standard deviation, defining features of that z-score distribution. And so what we get to critical pieces of information, we get the value. The value of a z-score tells us how many standard deviations from the mean that score falls. And then we've got a sign, the plus or minus, tells us position, above or below the mean. So a very, very efficient way of communicating quite a bit of information in a single score, which is really nice for us in terms of an applied statistics standpoint, right? So again, if we've got a normal curve here and I've got a z-score of 1, we're right here, right? We're one standard. If I say, oh, this score is associated with a z-score of 1, I know that value falls 1 standard deviation above the mean, right? Negative 0.5, here we got a half standard deviation below the mean. 2.5, I knew that someone is 2.5 standard deviations from the mean. And Mesa, if I'm out here at 2.5 standard deviations, am I starting to talk about a common score or uncommon score in this distribution? Pretty uncommon, right? And so now all of a sudden, if I understand kind of what the shape of this distribution looks like, I can take a look at this value and now start to make some inferences about the likelihood or rarity or commonness of that score, right? Same thing, -1. We're down here, Johnny. Is that what would you say about the how the likelihood of that score at a value of -1? It's pretty common. I mean, it's not as common as 0, right? But it's still within what we would expect of just sort of a general sampling. Okay. So formula for calculating z-scores, pretty simple and straightforward. Basic algebra, we just take, and remember that the order here starts to become important if you want your signs to come out right. We're taking the raw score minus our distribution, dividing it by the standard deviation, and what this is going to give us is a z-score. Okay. We've got want to find the corresponding z-score if I've got a raw value of 12, population mean of 10, and a standard deviation of 2. What's the z-score there, Johnny? Yeah. Okay. Uh-huh. Uh-huh. Oh, yeah, I don't care. I don't care about that. So in terms of like, how do we designate mean? In psychological science or in psychology, in reporting, you often see it as an italicized M. But in statistics, you'll see it as X bar. It doesn't matter, however you want to denote that. Okay. But also, Johnny, what's the z-score here? We've got a score of 12, mean is 10, standard deviation is 2, 1, right? I've got a score that is exactly 1 standard deviation above the mean. What about for X equal to 8? Yeah. What's that? -1. Daniela's got it. -1. We've got a standard deviation below the mean, right? 11, -0.5. We're just a half standard deviation below the mean, right? So simple math. I believe in you that you can do it sort of in your head, but on the spot. So there's some pressure there, right? So this is all pretty straightforward, right? But we can start to get into sort of more complicated situations. So here I've got X of 17, a mean of 34.6, and a standard deviation of 8.2. Not something I can easily do in my head, but if I go through and I say 17 minus 34.6 over 8.2, what does that give me in terms of my z-score? -2.145. Perfect. Yeah. That's a good question. That's a good question. I mean, when you're running your hand calculations, just in general, now this will change sometimes because if we're working with the very small values, right? Like if you got 0.00 something, then probably want to calculate that out. Doing hand calculations, if you're rounding to like the 3rd decimal, that's pretty good. We start to get into a discussion on significant digits. Who's heard of that or run into that before, right? Some more science thing talks about precision, right? Like, so this is the thing when I like sort of look at a manuscript and someone's reporting like age to the 4th digit, I'm like, I don't know that we need 4 digits on. So the person is like, really single digits is probably about fine with that, right? So wanting to think about what it is you're measuring, right, and how precise your measurement is. Generally, if you're reporting, if you're in your hand calculations, going out to taking things out to three digits, right, and making sure your rounding is correct, that gets people tripped up, right? 5 and above, you round up. 4 and below, round down, right? So just be mindful of that, because otherwise you get cumulative errors that then you get points flagged and things like that. In terms of reporting like coefficients and stuff like that, 2 is fine, right? But this is a thing to get into like SPSS and things along those lines. When you're reporting things, we report p-values like three decimals, right? So don't give me like 17 digits out there, because that's someone just cut and pasted viable reporting. So yeah, just in so that we're all on the same page and things like that, and particularly when we're getting for smaller numbers, those small sort of what you're doing can start to move things around. So good rule of thumb. Thank you, Gabe. Okay, cool. Everybody seeing where we picked this up? Okay, perfect. Thing to keep in mind is anytime we're doing any type of standardization, okay, our test statistics, our effect sizes, it's almost always this ratio for these means-based things. And then even as we go beyond, we've got a deviation score divided by a variance estimate, or well, it's not a variance. I mean, an estimate of variability. It's just a ratio, right? Start right now recognizing ratios, right? This is just sort of this much above this. And we think about looking at the z-score, taking the difference and then standardizing its units of standard deviation, right? So we've got a raw score of 17 minus the mean divided by the number of standard deviations. As soon as I do that, it's giving me a number that represents units of standard deviation, okay? This is going to come up again and again. Calculate the majority of our statistics. So if you start to become comfortable with that and sort of looking at those ratios and being, okay, this is what this means, your life starts to become easier, right? And so this is what I had talked about early on, not just looking at these formula as like, oh, this is what I plug things into to get a right answer, thinking about what this actually means. And that will help sort of build some of that conceptual understanding of what's going on with these statistics. Okay. So if we go through, and for this stuff, always good to graph it out. Okay. Sometimes if you're it's for functioning academics, right? So you draw out your normal curve, you sort of put your z-score units right here. We're at negative 2.15, which is right here. This is corresponding to our x value of 18, right? This tells us a lot of information about where this score falls, okay? Mandy, is this at not quite 2.2 standard deviations below? Is this a typical score in this distribution? No, it's not. It's out there towards the tail, right? So I can start to infer things about the characteristics of this score based on sort of that z-score, right? Just tells me a lot of things about this. Okay. All right. Other thing too, with a little bit of algebra, we can start to restructure this formula to start to solve for different pieces, right? So I could say, what's the raw score for z of 1.96 if the mean is 73.6 and the standard deviation is 14.8, right? So I know that I've got 1.96 equals x minus 73.6 over 14.8, right? This is just a basic solving for x, right? Has it been a while since people had solved for x? No? All right. Katie's been solving for x for forever, right? But so just 14.8, so cancel that. So to multiply those two, right? And then we just take this, sort of add on to, so then we got 14.8 times 1.96 equals x minus 73.6. So we take that and add 0.6. Right? So this, if we get, what's this number? 14.8 times 1.96 plus 73.6. 102.22. Okay. And now what we want to do, right, Mesa, is go through ability check. I know that I've got a standard is 74 and my standard deviation is 15. makes sense, right? So we're in the same ballpark. So always when you're going through and calculating things, do a check to say, like, does this conceptually make sense to me, right? And if it does, you're in a good spot. If it doesn't, maybe go through and check your math, right? But again, same thing, we can go through and sort of just flip this around. We say, if a population mean is 65 and a raw score of 59 corresponds to a z value of -2, what's the standard deviation, right? So again, we're just doing the same stuff, moving this around. If I got a population mean of 4 or a standard deviation of 4, raw score of 33 gives me a z-score of 1.5. What's the population mean? We can just start working back through this to sort of get those answers with just some basic algebra. Okay. Some of this stuff will be pretty easy and straightforward, but again, if you understand what's going on, if you get a nonsensical number or something that doesn't make sense, right? So here, if I say I know I've got a standard deviation or I've got a z-score of 1.96 and I've got a mean of 73.6, and I say the raw score is 54. Is that a reasonable answer to that? Why not, Kitty? So even without calculating, right? I'm looking for a raw score that corresponds to about 2 standard deviations above the mean. And if I know the mean is 73.6 and I get an answer that's 54, how do I already know that that's wrong? Yeah, it's below the mean, right? So what if I swap something around and got things down? And so I can't impress upon you enough with this type of stuff. This seems kind of trivial, but as you continue to work through so these applied analyses, always that plausibility check to say, all right, so given what I understand about what I'm trying to do, does this make some sense? And if it doesn't, then you're like, okay, so there we go. I've caught something that's not quite right. Yeah. Yeah. No one needs to memorize any formulas. There's no like high pressure situation like sort of the terrorists have taken over the building and someone's got a gun to your head and sort of wanting you to sort of crank out the formula for z-scores, right? That's a really poor action movie, right? And so you will, in applied settings, you'll always have access to your formula, right? And I'll give you formula. I don't want you to spend your time trying to memorize stuff because that's not necessary. But this is another reason why looking at those formulas carefully and thinking about what they mean conceptually and how they map onto the concepts that we're trying to calculate can be very helpful. Because when you get that formula sheet, that's giving you a wealth of information about stuff. So pay attention to kind of what you're doing and try and avoid just being like, oh, this is a plug and play. This is the dance that I do to get the answer, but I don't know if it was right when I get to the end of it because I don't understand the process. Yeah, Daniela, did you have a question? Okay. Yeah. So I've got, if we just take a look, we've got a z-score that's about 2, right? Which would say how many standard deviations above the mean does the raw score correspond to? Almost 2, right? And if I know my mean is 73, and if I get for my answer and calculating a number that's less than 73, then I know it's wrong because it's going in the opposite direction. Okay. And that's a mistake. Now that won't be exactly where you get, but if I swap that around and put the mean minus X, then that's going to reverse things. And so it's those types of things that you want to be thinking about. Is this reasonable? Is this plausible? Does this make sense? Okay. All right, cool. All right, so why this is helpful, z-score is giving us the exact location of a raw X within the distribution, okay? Distribution of scores, I know and the thing is when we're talking about z-scores, this is talking about z-scores as falling on a normal curve in these examples. Issue is to have a normal curve in order to create z-scores. Z-scores or standardized scores don't necessarily imply a normal curve. We can apply z-scores to anything, and we will apply z-scores to all different types of distributions, right? But it's still what it's going to do is that z-score tell you sort of where that score falls relative to everything else in the distribution. Okay. So here we say Henry's personality scores 87 on a measure of conscientiousness. extroversion, okay? Which prominent? What do you think, Abby? Is there any way for us with the information there to know exactly what's going on with this? What's that? Yeah, right. I don't have enough information here. So I know Henry scored higher on this conscientious than the extroversion, but I don't know what the means are for those, right? I mean, I can assume that they're all have the same mean and standard deviation, but that's not reasonable. There's no reason to assume that. And so I don't know relative to the rest of the population. I don't know where Henry is scoring higher on extroversion or conscientiousness. It depends on sort of what those distributions look like, right? But what we can do if we go through and calculate z-scores for the conscientiousness score, and we calculate a z-score for his extroversion score, now it's very clear to identify relative to the rest of the population, is he scoring higher on this measure or this measure? Okay. Other thing is think about, okay, we got Claire interested in creating a composite quality of life variable based on scores from 3 different measures. How might we do this? Yeah. Brilliant. Yeah, yeah. Just go through and why, Katie, why can't I just add up the raw scores on these 3 different measures? Why is that bad? Right. Yeah. Maybe the first 2 measures are mean score scale or something like that, and the last measure is like a 0 to 100 scale because the metric is sort of levels higher than the other one, right? And maybe that one tends to bias lower and sort of get something else. And so, but if I go through and I calculate z-scores, I can go through and maybe add those up and then say, all right, if I, in my conceptualization, all contribute equally to the score, and here we go on this, right? Now, analytical secret, did this for a paper at one point, right? But and so it's like something you can, right? Like that was the big reveal. We're done with class. Like, is that right? But like this is the type of thing you can do. There are better ways to do this, but sort of with the skills that I had at the time, this was an acceptable way to go through and do this type of stuff. So just thinking about sort of ways we can use these z-scores for our purposes. Okay. Now, if we're talking about our distribution of z-scores, again, we've been talking about, yeah, Johnny. Yeah. Yeah, if we're going to go through and do that, we were add up the 3 z-scores. Again, psychometrically, this is probably not it's better than some ways you could do it, but certainly not. If we start to get into psychometrics, it's not the best way. It's a pretty ham-handed way to go about things, probably, because then there are a number of different assumptions that you're making about that sort of approach that probably don't hold. But in the absence of sort of sophisticated statistical information or computational models and things like that, it's probably an okay thing. Then we would just go through and add those scores together, and then we would have a new distribution of my composite score that we could go through and take a look at. Yeah, does that help? Okay, yeah. Yeah, well, yeah, yeah. What you could do is, I mean, you could go through and say, so like conceivably, these measures would be getting at different pieces and parts of quality of life, right? And so like, oh, this one's kind of getting at the subjective piece, and this one's getting at a more like health related quality of life. And this is something. So what we want to do is kind of get representation for these. So we're going to go put them all kind of together in a composite. Now the downside is psychometrically, we don't know if that's all sort of happening. Sort of like what is going into my quality of life. do these all contribute the same, right? And so this is where like latent variable modeling starts to become, like if you wanted to do that, that would be the way to do it sort of appropriately. But just as a quick and dirty approach for sort of going through, I want to sort of combine all these to sort of get relative, I want equal contribution of each one of these three measures. It would be our way to go through and do it. Yeah. Mm-hmm. No, this would be like I got three different. I've got the QOLI and I've got the WSPX. Yeah, yeah, yeah. The thing is, we got subscales on there, then metric, and then that starts to become easier. Here, we've just got back. Hey, in our data set, we got three different measures. Doesn't make sense for me to run three different models on all the same outcome, maybe. So what I want to do is kind of try and put these together. So just thinking about how to go about sort of doing this type of stuff. And depending on sort of the area and the outlet, some people will be like, okay, cool. Like I got away with it. This seemed reasonable to me. But like if you get into a higher tier journal and something like that, they're like, I don't know, you're making a lot of assumptions about sort of your constructs and how those are measured. And so maybe you ought to take a different approach. But sort of just to get the scores in ways sort of that sort of accounts for or recognizes kind of what they're saying. Yeah, you could do something like that. Now the score you get doesn't mean anything. Like there's no like real applied interpretation that you could attach to that outside of this ranks people the rest of the distribution where they're at. Okay. So again, this starts to how do our scores map onto our constructs? And so that starts to get into some sort of complicated stuff, but some interesting things to think about and important things to think about in terms of and measurement and assessment and things along those lines. Yeah. All right. So thinking about z-scores, right? We can create z-scores from any distribution. Now, if we're talking about the unit normal curve, then we're talking about a very specific type of z-score fitting to that curve, but we can calculate z-scores for any distribution. It just means the z-score distribution just means that we've got a mean of 0 and a standard deviation of 1, okay? So if I wanted to go through, and you'll do this lots and lots and lots and lots, if I have a distribution of any scores, right? All I need to do is we'll go through and tell SPSS to go through and save z-scores for this, and what one of those scores, those raw scores from the mean of the sample divided by the standard deviation, and then I'm going to get a whole column of z-scores, okay? By definition, the shape of that z-score distribution is going to be identical to the raw distribution. It's not going to change it. It's not going to do it. It's not a transform. It's just rescaling my units in terms of standard deviation units. Mean is always going to be 0. Standard deviation is always going to be 1, okay? Going to have you doing this a lot when we get into actual applied screenings, right? I'll have you go through and calculate z-scores. And if you take a look at your z-scores and the mean of your z-scores is not 0 and the standard deviation is not 1, you've messed something up. There's something has gone wrong, okay? So again, just understanding the properties and using these as checks for plausibility of what I've got going on, okay? So if I go through and do this, what I get is a standardized distribution. And so all this is doing is my standardized distribution now has a set mean and a standard deviation set at sort of what I determined it to be. Doesn't change the shape at all. All it's doing is just changing the values to correspond to something that's easier for me to sort of deal with computationally or interpretatively. I don't know if that's a word, but you understand what I mean. Okay, so here, let's say we've got a set of raw scores, 0, 6, 5, 2, 3, 2. We know we've got a mean of 3 and a standard deviation of 2 in that set. So what we do, we've got our of raw values, our 0 score, the standard deviation and a half below the mean, z-score negative 1.5, right? 6, standard deviation and a half above the mean, 1.5, 1 above the mean, right? So we can go through and calculate z-scores for each one of those raw score distributions. And now I have a column of z-scores. If I go through and I take the mean and standard deviation of that column, what's my mean going to be? 0, what's the standard deviation going to be? If 0 or 1, what have I done? Something wrong, something screwed up, right? But going through and understanding this. Now, again, with this small set, here are my raw X's, and here are my Z-scores. Is there any difference? Same, okay? So this is a thing that really sort of will trip people up, right? Is because we talk about Z-scores and we think about Z-scores generally in terms of this normal curve, right? And that's useful in some follow a normal distribution, trying to assign exact probabilities, right? A lot of times we're talking about this in terms of hypothetical distributions. Our raw distributions that we're actually getting, we can calculate Z-scores for everything, but it doesn't change the shape of the distribution. Differences from then our raw scores a lot of the time. Okay. Questions about this? Okay. So again, so that I think the thing that hits me in terms of thinking about like an actual application of this, right? If I have a random sort of eating disorder scale or something like that, I don't know much of anything about eating pathology or the specific scales that are used to measure some of these types of things, right? And so if you, Lindsay, give me a score that says back, oh, they got a score of 43 on the XYZQ, that means nothing to me. I don't know, right? But if you were to take that score and use some normative like treatment sample or something like that and create a Z-score, now all of a sudden I know exactly where that falls relative to the population of interest who I might be interested in as people seeking treatment for eating pathology. Now we've taken a raw score that means nothing to me and turned it very quickly into something that conveys quite a bit of information, right? And so this is how we're thinking about using some of these scores to communicate information to people who are sort of looking at our analysis and reading and things along these lines. Standardized distribution, or Z distribution, is just one of an infinite number of standardized distributions. I can have standardized distribution standardized to anything if I want. But when we look through research, we'll see different types of standardization T-scores. Has anybody ever sort of with, have you in the past seen T-scores with? Like MMPI and stuff like that, we'll use some T-scores and things along those lines. Katie, did you have a different example? Okay, okay. So now we've got a T-score. T-score is just a same distribution. It just has a mean of 50 and a standard deviation of 15. SAT scores, mean of 500, standard deviation of 100. We can play around with this all day. Like these are just standard metrics that people, for whatever reason, have decided to use. But like the mean and the standard deviation and transforming them into distribution we want, just using a few different steps. First, what we would always do is take our raw scores, determine based on whatever mean and standard deviation we wanted to use. Okay. So, for example, let's say I have a set of exam scores. I want to have standardized to mean of 500 and a standard deviation of 100. Okay. Distribution of raw exam scores had a mean of 57, standard deviation of 14. Calculate my standardized scores for these scores here, right? So if I go through same thing, I've got my column of raw scores. Okay, what I would first do, transform these into Z-scores, right? Going through, and so here I've got a Z-score of 5 units or a half a standard deviation above the mean, standard deviation below, right at the mean, standard deviation above, right? So now I've got my Z-scores. Now I just need to change that over to have a mean of 500 and a standard deviation of 1. So here's our standard deviation of 100. So here I'm half a standard deviation above. So if the mean, so if my mean is 500, I just take half of that and I'm at 550, right? Here, standard deviation below, Mean is 500, now we're at 400. Right at the mean, 500, standard deviation above, 600, right? I mean, these are pretty easy to go through and do in our head, but sort of again, using simple formula, we can go through and calculate all this stuff. So again, the z-score is the intermediary. If I have some distribution, and this, you won't do a lot of this stuff. This won't come up a ton, but it might come up in some areas, right? And so just wanting to understand how we're getting some of these scores and how we can move back and forth between raw scores and standardized scores and alternative standardized distributions easily using our z-scores. So it's a nice kind of intermediate tool. Okay. People see how we're doing this piece of things here? All right. If I want to do this sort of on a curve, drawing it out, again, this is a way that I think is helpful. So we're drawing my normal curve because we're assuming that we've got a normal curve for like SAT scores or something like that, right? And so here's my z-score distribution, here's my raw score, here's my standardized score. So I can go through and start to check sort of where my scores are. Does this all make sense? Plausibility to make sure that I haven't gotten something turned around. Things. Okay. Okay. So again, this is a lot of just playing with numbers to change the scaling on some stuff, right? But this ends up being more than a parlor trick of just something to do, right? Again, what happens is these z-scores allow us to compare scores in the distribution to start to infer some properties, characteristics of sort of whatever score that we've pulled. But if we're working with a standardized score from a known distribution, what we can start to do is start to infer probability about obtaining a score of that value or higher, okay? The key situation here is a known distribution, okay? This is what all of our inference tests is based on. We're calculating test statistics with known distributions, right? So if I'm calculating a t-test, I know that t-scores fall in a specific distribution, right? If I'm calculating an F statistic, I know F's fall in a specific distribution. If I'm calculating chi-squares, I know chi-squares fall in a specific distribution. Now that distribution is a theoretical mathematical property of this set of scores based on some basic assumptions. Now, if I start fooling around with these assumptions and changing things up, what happens to my distribution? It starts to change shape, right? And so now what I'm doing is I'm sort of making assumptions about this test score that's been pulled from sort of some conditions that violate some assumptions. And I'm thinking like, oh, I'm assuming that this distribution, the distribution of this test score follows a chi-square distribution, but it might not because I violated 7 different assumptions. So now that test score follows some distribution, but it's not the distribution that I'm sort of thinking that it does, or I assume that it does. And so now what happens if I start assigning probabilities, then I'm off base, right? I lose validity of my inferences based on this, okay? But when we do it right, and we're not violating assumptions, and we have some value or some statistic that falls on a known distribution, what's really valuable is we can start assigning probabilities to the likelihood of obtaining this score, okay? So here we've got our normal standard deviation units out. That starts to correspond to probabilities of sort of different areas under the curve. Did anybody make it to Calc 2? Okay, made it to Calc 2. You could make it beyond Calc 2? What's that? Okay, well, I don't know, like, so maybe there's like up top. This is the thing, like, I don't know, it's like sort of maybe there, I'm sure there are people at Harvard who don't take Calc 2, right? Right? So yeah. Anybody else sort of got, I mean, I got there just because I started out as an engineer, and sort of they kind of made me sort of go up through that sort of ranks. It's not like okay. But it's sort of at this level of math, right? Sort of the whole sort of purpose of sort of that level is sort of strategies for finding area under the curve, right? And so I was taking Calc 2 the same time I switched over and decided I'm like, hey, I'm out of this engineering thing. I'm in psychology, but I might as well just continue to sort of this in anyway, right? And I'm like, it was fun because I see exactly what's happening here in terms of sort of how these things are crossed over, right? Um, when we're looking at frequency distributions, these are directly related to probability estimates, okay? And what we're looking at is areas of frequency underneath sort of a hypothetical curve that are going to correspond to the likelihood of randomly pulling some score of a specific value or higher, okay? And because we've got proportions and probabilities are the same thing, right? What we can start doing is representing certain probabilities as areas underneath a graph, okay? So if I've got a population of scores here, I've got 1, 1, 2, 3, 3, 4, 4, 4, 5, 6. Okay, then that's my set of scores. A very small set of scores, but if I go through and create a frequency graph of these scores, right, and I can start asking, what's the probability of randomly selecting a score greater than 4? Okay, someone like, so what's my probability of getting a score that's greater than 4 here? What do you think, Gabe? What's that? 20%. Yeah, exactly right. How did you get 20%? Yeah, no, I did too. Yeah. And so how did you get 20% from there? Yeah. 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 So we've got 2 boxes that are greater than 4. We've got 10 total boxes. Get that into a proportion, which is the same thing as you know, a probability statement right here. And so the likelihood in this set of me grabbing a score, randomly selecting a score that's greater than 4 is 20%, right? Do people see kind of how this sort of frequency distribution is corresponding to a probability? Following along with this? Okay. What we're doing then when we're running into statistics is we're sort of taking this and kind of ratcheting it up, right? We don't have 10 scores, we have conceivably an infinite number of scores, right? And if we graph the frequency distribution of this hypothetical distribution of scores, what we get is sort of a distribution that follows some specific characteristics. And if we have a normal curve or a normal distribution, what we see is we get a distribution that's symmetrical. We get highest frequencies in the middle. Things taper off as we move out. Mean, median, and mode are all sort of identical, sort of in the middle. Now we can have other types of distributions that follow these properties that aren't unit normal distributions. We have T distributions and things along those lines. But if we're talking about a unit normal distribution, that is a very specific distribution that has very specific characteristics. And because we know those characteristics, what we can do is we can start identifying areas under the normal curve as being associated with specific probabilities, okay? And our z-scores here are standardized units that start to mark specific areas that we can start to then infer probabilities from, okay? So again, 20% here, but what I can do if I'm looking at, let's say we've got this distribution of introversion scores, what I can start doing if I know what that distribution, if I know that introversion in the population as measured by this instrument follows a normal distribution, money, because now I can go through and start assigning specific probabilities of people having certain scores or higher, just based on sort of what I know about this normal distribution. All right, so here's my normal distribution. You've probably seen this or familiar with this. We've got here mean of 0, right down the center. 68.3% of, in a normal distribution, 68.3% of scores are going to fall between a standard deviation above and below. If I go out to 2 standard deviations, I've got over 95%, right? We've got 2.28 in sort of the tail of that distribution, extending beyond 2, same thing on the other side. The symmetry of this makes things nice, is because if I sort of know from the middle out, then I can infer the same thing about the other side, right? And so what we do is we've got a really nice distribution with known properties associated with known probabilities. So if I ask Johnny, what is the likelihood of randomly selecting a score that's more than 2 standard deviations below the mean if scores follow a normal distribution? Yeah. Randomly selecting someone who scores less than 2 2 standard deviations below the mean in a normal distribution. Yeah, 2.28%, right? There's nothing over there on the negative side, but we know it's symmetrical, so we just go over to the opposite side, okay? Lindsay, what's the likelihood of me randomly selecting a score that is either 2 standard deviations above or 2 standard deviations below the mean? Yeah, we just double that up. We'll call it 4.6%, right? And so what I can start doing is sort of looking at the likelihood of randomly selecting a specific score of certain characteristics, or the likelihood of sort of these scores just emerging naturally. So here, when I'm looking at things, having a score that falls within a standard deviation above, standard deviation below, pretty common, right? About 2/3 of my, a little over 2/3 of my scores are going to fall there. As I start getting out and farther, events start to become more and more rare. Not impossible, but start to become increasingly unlikely as we go out towards the ends. Okay. Right, this is our formula. In case you wanted to know the mathematical formula for the normal curve, this is what that is. And so if we have a distribution that follows that property, or sort of follows this formula, what we know is we can start to assign very specific probabilities for events occurring at sort of certain different z-scores, okay? What happens if we have a curve that doesn't follow that distribution? What do we got? We got a paranormal distribution. This is different than what we'd thought. It was not the same. And so it has that are mysterious to us, right? So beware of our paranormal distribution, but this is the normal distribution, okay? And this is the whole thing. All of our statistics based on this. We calculating test statistics that have known characteristics, and as long as we know those characteristics, we can start assigning the likelihood of events to those things. But as soon as things start to deviate, or we start to violate assumptions, and it starts to change the characteristics of that curve, now we're in a situation, if we start to apply those normal theory statistics to something that doesn't follow that, now we're saying, oh, this is the likelihood of this event occurring. That's actually not the occurrence, because we're not following that we think we're following here. So if we're going through, and so we start to go through and use this, we say adult heights has a normal distribution with a mean of 68 inches and a standard deviation of 6 inches. Given properties in the normal distribution, with the probability of randomly selecting an individual at or taller than 80 inches, about 6'8". Okay, so already, just given what you know about people's height, is this going to be a high probability or a low probability? Low probability. Like just randomly grabbing someone who's 6'8" or taller is probably going to be a low probability event, right? What we can do is we can start to say not just low probability, I can give you the specific probability of this, right? So if I go through and I graph out my normal curve, okay, and I've got a mean of 68, standard deviation of 6, so 74 inches is a standard deviation unit above 80, that's 2 standard deviations above, okay? If I go through, calculate my z-score here, so 80 corresponds to a z, 2 standard deviations above the mean. And then what I can do is start to go through, use my unit normal table to find the specific probability of interest, okay? And what we're going to do with this is go through and just grab a unit normal table, okay? Now I said, do people have your unit normal tables sort of up and taking a look at this? Okay, so here is, and you'll get different unit normal tables that have different characteristics. The one that is included here that I've sort of added in is sort of as the PDF. This is kind of nice because here we have the z-score, right? And then here we have a column that gives us a proportion from the mean to the z-score, right? So from the mean to z, we've got a probability of about 0.14, right? So between 0 and a z-score of 0.36, the area under the curve here is 0.14. It corresponds to 14%, right? Larger portion, if I go through, calculate my z-score, Larger portion is the body, right? That's the bigger piece. Smaller portion, this is the tail, okay? So when you're going through and running these problems, always make sure that you're going through, drawing this out, finding your z-score, and then deciding what's the problem asking me. Is it trying to find something in the body or the tail, right? And so this y column, you can ignore that. That's the sort of height of the slope. You don't need to worry about that for the stuff that we're doing, okay? But it's a pretty slick table, pretty easy to use, and recognizing that here is our z-scores, that's telling us how far